Yeah, timer is running, so okay, that's all. So now you will need to practice a lot on this to get yeah, to be confident. You must practice a lot on this. uh, so so we have already discussed basically, if in short, if I have to talk about point groups, these are the points: non-axial, cyclic, dihedral, polyhedral, and linear. So non-axial is having least number of these symmetry elements. So C1 nothing except identity operation, identity thing. CS only plane, CI only I, only inversion center is there. And then cyclic groups are those in which have this rotational axis Cn, and you can have, in addition to that, if you have vertical plane, horizontal plane, so try to find out. And if a molecule has both the horizontal and vertical, you will go by the horizontal planes. So dihedral, it means you have a literal meaning of dihedral is two-headed, two heads. So it's a so this comes from so this means that you have a Cn axis, and perpendicular to that you have n number of C2x, n C2 perpendicular to Cn. This is the identifying feature of this. And then you can have, in addition to that, if you have uh, sigma d dihedral plane or horizontal plane sigma h, so accordingly the groups are classified. And then at the other extreme of these things are the groups which have a large number of symmetry elements are present. So tetrahedral, a regular tetrahedron TD, a regular octahedron you have OH. So and in icosahedron you have, yeah, so IH. So like that you can have so, and then you also have linear molecules such as CO, which will be seen like this, if C infinity V or something like that, is like that, because there is no horizontal plane. But if you have an example of say N2O2 or something, any other CO2, they will be having D infinity H as the point groups. Why? Because the molecular axis that you will take for the linear one, you can rotate by any angle. So the highest order axis is infinity. Okay, so n is infinite, and that's why we call it as mm, so uh, so symmetry elements and operation defined by groups and behavior. So their behavior is dictated by group theory. Why is it like this? एक बार और अभी किया था, कट रहा है फिर. So next we so this is the point that you should be now able to identify the symmetry elements present in a molecule. And once you have identified the symmetry elements, you should be able to find the point group. Okay, so water, if you now, so taking example of water, it is easy to go further. So if you have water molecule, you identify a C2, and then you have a sigma V. There's two type of vertical planes. We have already discussed these things. So looking at it, you can easily identify sigma V prime. So two vertical planes. When you have ammonia, this is the ammonia. So you have three vertical planes, sigma V. So C3V is the plane like this, you can identify. Then if you are having a typical molecule like this mx4y2, so what is the, so you have a C4 axis, and you also have a horizontal plane comprising of this and a C4 passing through this C4 axis. So perpendicular plane, n number of C2 axis is also there in the perpendicular plane. So it is D4H groups. Uh, so so there, for highly symmetrical molecules, as I told you, they are identified such as tetrahedrons and octahedrons. They have their own point groups, TD, OH. These are the most common ones that we encounter. So the steps are like this: determine the structure by Vesper theory, and then find out all the symmetry elements present, follow the flowchart, determine the point group. Later on, when you have with little amount of practice, you will realize that you don't even need the flowchart. बाद में आपको flowchart की भी ज़रूरत नहीं पड़ेगी और आप देखेंगे बहुत आसानी से point group determine हो जाएगा. So example, what symmetry elements are present, you identify them. So amongst these molecules you try, so you will find that 3 molecules have same set of symmetry elements, and they belong to one point group C2V. So this was the scheme that we had to follow. So first you look for the axis, highest order axis, then whether they are n number of C2 axis perpendicular present or not, and then you follow these steps, and you reach to a, okay, uh, so these are the examples. Determine the point group for each of the following molecules: 1, 2, 3, 4. So if you have to follow, so first example, so first thing is that you should be able to visualize 3-dimensional कैसा दिखेगा मॉलिक्यूल. वो जब आपने विजुअलाइज कर लिया है तो काफ़ी आसान हो जाता है. So just, yeah, visualize it, close your eyes, visualize this and see the molecule. So once you are able to do that, you can find the axis, rotation axis, mirror planes and everything. Okay, so what we do, so you have two cases here. This is trans, this is cis. Now what are the symmetry elements present in cis and trans, you can find. So here again Mn, this is eclipsed configuration. So eclipsed configuration, one over the other, like all the points of this plane and all the points in this plane, they should be just superimposed over the other. That's how you have to visualize. Okay, so like connecting the two octahedron by the along the that axis, the main axis that is there. So along that, if you are connecting it, so like it is like just like that. And this is this ferrocene molecule that is again staggered. So starting with this, find the highest order axis in this. What is this? So you can imagine where is the, so what do you see? Do you find your axis? Yes. So you can find the highest order axis, n is 2. Which one? एक जो होगा यहाँ पे होगा सेंटर में, above the plane of the, so coming out this screen, आपके मोबाइल स्क्रीन से या लैपटॉप के स्क्रीन से बाहर आता हुआ यहाँ पे बीचों बीच एक पॉइंट, एक लाइन हो सकता है. So that is one you can visualize, and that is the C2 axis. Then there are n number of C2 axis in the perpendicular plane. Is it, or yes or no? So that you have to find if it is. So n number of C2 axis in the perpendicular plane. No. Then you move to the next. Is there any the mirror plane perpendicular to the principal axis? So just so perpendicular axis, do you have a mirror plane? So just try to see. If you do have, then so this is something that you should be able to. So that's how you label it C2H. So once you have realized this, you can reach the answer easily. Okay, so C2H. So like this, if you can, so if you are able to see this, so next go to the next. So this is a cis configuration. Now if you try to see, so N2 still you can have see that you have a C2 axis or not. Are there a number of C2 axes perpendicular to this plane? No. Then is there any mirror plane perpendicular to the principal axis? No. Any vertical mirror planes? C2V? Yes. So C2V is the thing. So it is the flowing through the going by the flow chart. Similarly, take this molecule. So the previous case was C2. So this was the eclipsed configuration that we were talking about of manganese Mn2CO 10. So this is a metal bond you can see here, Mn bond. Okay, anyway, we are concerned with the structure only at this point. So you can find the highest order axis. This is N4, N is equal to 4, cutting across this. N number of C2 axis, perpendicular, yes. Is the mirror plane? Yes. So it will be C4, so and then horizontal, so D4H. So this is how you have to do it. And if you are looking at the this ferrocene molecule, N is equal to 5, cyclopentadienyl C5H5. So N number of C2 axis, yes. 5 C2 axis you can find in the perpendicular plane. Is the mirror plane perpendicular to the principal axis? No, there's you won't find that. Are there dihedral planes? D5D. So this is how we do it. So if you are so D5 ferrocene, D4H. So are you able to visualize all this, or you need to go to the that thing C2B, C2H? We can try this. Type simotter.org/gallery. Okay, so it will take you to the website, which is okay. So identify by pointer. So see here also the arrangement is like this: the non-axial groups, the linear groups. So we can have a, so we were talking about C2H. So similar to this, you have, this is the example that we were discussing, right? So can you visualize this molecule now? Are you able to see? So this was the molecule that we were first taking, example of C2H. So can you correlate these things now? So this one, okay, so just instead of a methyl group, you have fluorine placed over there. So you can see the similarity that we have. So this was the molecule. So what was the highest order axis? Highest order axis, you can find out the principal axis is C2, this axis, and yes, the other points are, you can find the sigma h, sorry sigma h कहाँ गया, सिग्मा एच ये है. सो C2H सीधा हमको दिख गया कि C2 है, H भी है. C2H पॉइंट ग्रुप इसका पहले ही पता चल रहा है. n नंबर ऑफ C2 एक्सेस नहीं है. देयर इज नो so in the perpendicular plane you do not have n number of C2 axis. This is the another one, and this inversion center is here. So this is central point, which is center of inversion. Through this point you can take it across, and you can have the same set. So inversion center है, यही हमने देखा था. और क्या था, C2 इसी का C2V वाला होगा, सिस ग्रुप. सिस में यही चीज चला जाएगा, तो ये सिस हो गया, उसी का सिस वाला वर्जन है. ठीक है. सो इसमें भी आपको एक C2 एक्सिस होगा जो उसी प्लेन में, उसी में है. ऊपर से नहीं देख सकते, ऊपर वाले प्लेन में C2 नहीं, ऊपर से नहीं है. ये है C2 एक्सिस lying in the same plane, and then you have the same, it also contains the reflection plane, one plane containing that axis, another plane containing the same axis. So both these are vertical planes, not horizontal planes. Okay, so C2V. Okay, so this is the point that we have seen through our this. Then you wanted to see about the dihedral ones. So we had seen this ferrocene DND type, anti-prismatic, it also called. So ethane staggered and फेरोसिन अभी हमने देखा. फेरोसिन को भी हमें, वी हैव स्टैगर्ड फेरोसिन. सो ऊपर वाला देखिए, सामने से देखिएगा, उसका जो 5 पॉइंट है, उसके नीचे वाले जो प्लेन में 5 पॉइंट है प्लानर, वो कोइंसाइड नहीं कर रहा है. स्टैगर्ड का मतलब यही होता है. इक्लिप्स में एकदम पेंटागन, एक पेंटागन का सारा पॉइंट्स नीचे वाले पेंटागन के ठीक उसके ऊपर आएगा. दैट इज इन एक्लिप्स्ड. But this one is staggered, so we have to make a pentagon, one pentagon which is above, another pentagon which is behind the screen, and that is not coinciding, the points are not coinciding with the upper ones. So in this you can clearly see a C5 axis, C5 axis, this one. So when we draw in a two-dimensional plane, you can just simply denote by a simple dot, just like dot. It will appear like a dot, dot जैसा दिख रहा है. तो आप पेपर में भी जब बनाएंगे कि ये C5 एक्सिस है, you can show that this dot resembles that line which is coming out of the screen, coming out of the paper. ठीक है ना, जब इसको मोड़ते हैं तब ये ऐसा दिखता है ना. अगर हम ऐसे रखेंगे तो ये डॉट की तरह ही मुझे दिखेगा. ठीक है ना. सो जस्ट लाइक दिस. So this is one axis that you see. Then you also see there is no horizontal plane in this molecule, but there are dihedral planes. So each one of these are dihedral planes. So 1 2 3. So you saw this 1 2 3 4, 5. 5 dihedral planes. Dihedral plane is there, but there is no sigma s, there is no sigma v. We call it dihedral because it bisects the C2 axis, which is in the, yeah, it is. So dihedral planes are the ones that contain the principal axis, but they are also bisecting the two C2 axis that is lying in the plane. So just one thing you can have. So if we can have, so these are C2 axis. So why we are calling it dihedral? Because in the perpendicular to the principal axis C5, this plane cuts the angle between two C2 axes. So that's why it is a dihedral plane. Okay. So you can see, so this is why you have 5 C2 axes along. You can visualize the 5 C2 axis coming from all these points. So is it 5 C2 axis? आप ध्यान से देख सकते हो कैसे बन रहा है. You can point it out like that. So पेंटागन के हर बीच से जहाँ पे वो ओवरलैपिंग पोजीशन, दोनों पॉइंट्स जो इधर है इसके बीच से एक लाइन गई है जो C2 है. So if you want to see each one of them, simple way, let me take this out, just one. So if this is a C2, rotate it and by 180 degree along that line. If you can visualize another one, so these are the points C2 representing C2. So n number of 5 C2, so D 5 D, that's how it is coming. So इस तरह से करके हम आगे बढ़ते हैं, सारी चीज़ें विजुलाइज करने की कोशिश करेंगे, and you will find it pretty easy to find. So एक बार you have got the picture of a molecule in the mind, you will be definitely able to find the point groups. Okay, so we have now known that what is low symmetry, high symmetry ones, so all these things. So only mirror plane is there in this case, CLBR. So you can also see that a tetrahedral one which is having, okay, one more interesting point, if I can, yeah, just came to my mind. Yeah, you can visualize so you think of a CH4 molecule, then suppose we replace it by one CH3Cl, CH2Cl2, CH. Hello. No, 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 वही है. So if you have, so we are talking about this CH4. So CH4, you clearly know that this is a tetrahedral, regular tetrahedron with so this is so structure that I told you to visualize, that you have to, if you draw, so there are 2-3 different ways, one of which shows you like this. So wedge type to show that these are the bonds which are outside, and so shade it this part, and you have the behind the plane you have another one which is shown by this. So all of them, so this is a regular tetrahedron, you write it, this is, there is no confusion about it. What about this? So as you go on replacing this, so symmetry elements present in this molecule is very large. You have so you have so we have discussed the tetrahedrals, and we found that there was large number of symmetry applications. But once you replace one of them with Cl, so imagine this Cl, and now try to find the point groups for this particular molecule. So it is like, so what is this? What is the point group here? What are the symmetry elements present? And then when you replace it with C, Cl, so can you visualize now what is point group? क्या होगा? What is the point group of this? So if you go on replacing from a high symmetry structure, a regular tetrahedron, when you replace it by the hydrogen with a chlorine, with one chlorine, two chlorines, then it becomes, what do you, so yes, अब बताइए क्या होगा point group? What is the point group of CH3Cl? How do you start with this? Find the highest order axis. What axis is present in this molecule? C3 होगा, C3 एक्सिस दिख रहा है, और C3 के साथ आपको you are also having sigma v. Yes, 3 of them, right? So इस तरह से आप सोचेंगे और you can easily account for the point group. So this is C3v, और यहाँ पे ये थोड़ा सा देख लो, हाँ इसको आप C2 होगा, वाटर, हाँ उसको आप अपने तरह से उसको डिजाइन कीजिए मॉलिक्यूल को। मतलब अगर आप इसको इस तरह से देखें, C and H इन द प्लेन, या दो प्लेन के बाहर आ रहा है अगर, और ऐसे भी हम इसको विजुलाइज कर सकते हैं कि दो इधर और दो पीछे की तरफ अगर जा रहा है, ऐसा भी आपको दिख सकता है। और थोड़ा सब एक प्लेन में नहीं है, अगर ऐसा होगा तब भी एक टेट्राहेड्रन हम ड्रॉ कर सकते हैं। So CH2Cl2, it will have yes, and then if you have visualized this way, then you can, it becomes easier to find that you have a C2 axis here. So now if you do a 180 rotation along this, then you have C2, and containing that you will also have, you can sigma v. So you also have 2 sigma v planes, so it is C2v. So आपने देखा कि gradually when we substitute in a tetrahedral geometry, we change the substituents of the in CH4. Gradually we are moving to lower symmetry, and when we have all the symmetry elements are different, तो वो पूरा C1 बन जाता है. अगर सब अलग अलग all the substituents are different, then it is absolutely no symmetry. You have C1 that is formed. So इस तरह से थोड़ा सा देख सकते हैं. कहीं किसी भी ऑक्टाहेड्रल में स्टार्ट कीजिए, एक ऑक्टाहेड्रल ML6, नाउ चेंज इट बाय L1, L2, L3, different types of ligands are there. Then again the symmetry elements will be less, and you are moving from a high symmetry structure to a low symmetry structure. So this is one thing that I was trying to make out, point to be noted. And flowchart is here. Besides, you will have to be very careful when solving problems. कई बार होता है कि आपको एक स्ट्रक्चर दिया होता है, या कहा जाता है कि सिस कन्फर्मेशन का बताना है, ट्रांस का बताना है, या किसका बताना है. और कई बार ऐसा पूछा जा सकता है कि जस्ट H2O2 मॉलिक्यूल का क्या होगा. तो उसमें जो अगर इफ यू हैव नॉट बीन आस्क्ड what is the confirmation is not given in the question, then you have to go by your own instinct, find the most stable form by Vosper theory and other whatever you think of, how the stable structure is arrived, and then assign the point group. The question may be asked that no, we want to know what is the point group in Gauss structure of H2O2, or what is the in trans structure of H2O2. Then you have to accordingly find out, imagine the geometry, and then work out. So for example, H2O2 can exist in can have 3 different conformations. So इसको आप इस तरह से देखिए, ये बुक, ये जैसे हुआ ना बुक, just imagine you have a book, and at the book you look at this is oxygen, this is another oxygen, and they are forming the that main hinge, जहाँ से वो खुलता है बंद होता है, वो जो लाइन है. सो ये बुक की लाइन, और इसके पन्ने, look at the pages. If you have a book, these are the pages, and one of the page is having H bond, this hydrogen, look at this. Another page you have H hydrogen. Now you completely open the book, so that is the trans. Okay, if you now slightly keep the book in try closing the book, but do not actually close it completely, that one is the Gauss. And if you close the book completely, imagine this is a book and you are trying to close it, so that will be, if you close the book completely, then it will be cis conformation. So it has been found experimentally that it is the Gauss conformation, this particular picture, is the most stable form of H2O2. And so in Gauss conformation, because although if you are looking at the from point of view of repulsion, electronic repulsion that I told you in Vosper theory, so looking by simply by repulsion, this should have been more stable. But in this case, the Gauss conformation is found to be more stable. The explanation for that is that there is possibility of hyperconjugation between this thing, hydrogen at C and H atoms, sorry, O and H atoms, when they are slightly closer in this manner, and that gives additional stability. Whereas in cis condition, there is huge repulsion again between the pairs, bond pairs, and that will destabilize the system. So cis is having high, as I told you, maximum repulsion, so maximum energy. Trans, although it has they are far apart, the repulsion between bond pairs is less, but there is loss of the hyperconjugation, which was a stabilizing factor. And the Gauss, it is more stabilizing, although there is little bit of repulsion, but hyperconjugation is giving you additional release of energy, more stabilization, greater stabilization due to due to hyperconjugation. So you will find that in some of the net exam they had asked what is the Gauss conformer or something. किसी का पूछा गया था कभी, तो आपको क्वेश्चन बहुत ध्यान से देखना होगा कि क्वेश्चन के अंदर ही तो कहीं कंफर्मेशन नहीं इंडिकेट किया हुआ है। अगर कंफर्मेशन इंडिकेट किया हुआ है तो उसको फॉलो करें, अगर नहीं किया हुआ है देन यू गो बाय योर ओन इंस्टिंक्ट, फाइंड दिस मोस्ट सुटेबल structure of lowest energy and tell about that. So now you can easily, if you find all this conformation, for each of these conformation you can assign the point groups. Okay, C2V, C2. So the Gauss conformer is the least symmetric. So most symmetric structure is this one. You are having large symmetry element C2 and C2 and H. Horizontal plane is there. Besides the, in this case only the vertical plane is there, and in this case the vertical plane is gone. So only CN axis is there. So this is the case of for the point groups of H2O2, because yeah. So this the idea of symmetry, the knowing the point groups helps you in lot of things that you will realize later. Of course, it helps you in bonding. It also helps you in knowing the polarity and chirality of a molecule. So you can, by knowing the symmetry elements present, it is possible to predict whether the compound will be optically active, whether it will be polar or not. It is likely to be polar or not. So that is the one thing that we have to understand, that whenever we carry out symmetry operation, it must not change any of, so the operation itself should not change the physical property of the system. So this has important uh, consequences on when we try to predict chirality or polarity based on point groups. So when we are talking about polarity, so a molecule is must having a permanent dipole moment. So in what conditions they can have permanent dipole moment, that you should understand. So any asymmetric charge distribution will result in developing a dipole. So usually it is the asymmetric distribution of electrons. Okay, so the point group of the molecule uh, can tell you that whether you can have a molecule may have a dipole or not. So it can have or cannot have. It can also tell you that in which direction it will point. So here is the thing. If a molecule has Cn axis n greater than 1, of course C1 has no meaning. In fact 360 degree rotation is nothing. So it cannot have a dipole moment perpendicular to the axis of rotation. So if you have a Cn axis and perpendicular to it, if you rotate it, then dipole moment will change. One thing that we have just said, so remember what we have highlighted, there should not be change in the physical property. So if you have a dipole moment perpendicular to the Cn axis, then one rotation and the dipole moment will change. The direction of dipole moment will change. So a positive value it may turn to a negative. So that is not allowed. So it is, then it will not be a symmetry operation. So any symmetry operation should not change the physical values, physical parameters. So that's why if you have a Cn axis, the dipole moment cannot be located perpendicular to the axis of rotation. So C2 rotation would interchange the ends of the dipole and reverse the polarity. So which is not allowed in a symmetry operation. So you cannot have a dipole in the perpendicular plane. So at that, the conclusion is that any dipole that may have may be present will lie only along the CN axis. Only along this principal axis you can have a dipole. Now an symmetric operation, so now when it is a principal axis and you rotate it, there is no change in the position of the atoms along that axis. So that particular thing is likely to be, so for example, if you think of water, and this is the C2 axis, and if you rotate it along C2 axis, then the net dipole, which is was pointing along C2, so net dipole in this case is pointing along from positive charge to negative charge, so net result is pointing this way, and this is lying on the C2 axis itself. The dipole moment is along C2. The dipole moment is along C2 axis, and so it has no effect, is along C2 axis, and C2 axis पे है और not affected when rotation is done. So इसको कोई असर नहीं पड़ता है जब आप C2 पे कितना भी रोटेशन कीजिए, कुछ नहीं होने वाला. Dipole moment is still intact, and we are satisfying the important condition that asymmetry operation should not change the physical property. So a C2V point group, C and V point groups are likely to have polarity, likely to be polar molecules, but polarity, yes, so this is one point. So if you think of yeah, so any molecule that has polarity, permanent dipole moment, you check it, you will find that the dipole moment is now lying along the principal axis. आप reverse में check कीजिए, you go apply the reverse concept, check all the molecules which are known to be polar, find out the direction of dipole moment, whether they are lying on the principal axis or not. You'll find that it is definitely the case. In all the polar molecules, you will have the dipole moment, permanent dipole moment, which is lying along the principal axis, CN axis. Okay, so so dipole must lie along the CN axis. It cannot lie perpendicular to the CN axis, the principal axis that we are talking about. So interchanging of the two ends, because any rotation, 180 rotation will change the positions, interchange the positions, and dipole moment will be affected. So only groups that can have dipole moment turns out to be CN, CNV, CS. देखिए कितना आसान हो गया. So now you got it very easy. CN or CNV, you then it becomes easier to tell which will have. So a non-polar, so C okay, CN, CNV, like this. So these are so dipole moments perpendicular to the polar molecules cannot have a dipole moment perpendicular to any mirror plane or axis of symmetry. So again, mirror operation should not change the thing. So perpendicular mirror plane जिसमें भी होगा उसमें नहीं होगा dipole moment. So if you have a molecule, so visualizing as H2O2 we have just discussed. So if you in a C2 geometry, you have C2 with a mirror plane. This is a trans thing, and this was the Gauss conformer that we were talking about. Dipole moment possible because it is parallel to now C2 axis. So it is, in general, we are not indicated any atoms over here, but it will depend, the direction of dipole will be either this or this depending on which atom is connected over here. So any molecule with CN axis perpendicular to the C2s and having perpendicular C2 axis or sigma h plane cannot have a dipole moment in any direction. Very important conclusion. Any molecule with a Cn axis and perpendicular C2 axis or a sigma h plane cannot have a dipole in any direction. So all d point groups non-polar, all cubic point groups icosahedral, octahedron, tetrahedron are non-polar. Okay, and look at this. This is a C3V. So now there's also one more important point that I would like to point out. This only tells you that what groups can have based on the structure. uh, Simply geometry, we are saying that these groups Cn and Cnv are likely to have dipole moment, permanent dipole moment. But there's one more point of caution. एक और ध्यान देने की बात है कि dipole moment also depends on the nature of the bond. So if the electronegativity difference is less or something, then the dipole moment, although it is predicted by the point group the way we have analyzed, it may be less or it may not be actually present. So that kind of case you can encounter here. If you compare NF3 and NH3, you will find that you can also say that we are only saying they must be polar. I am not saying. We are saying they can be polar. So a CNV point group is likely to be polar, but what will be the magnitude, which we are not sure. And in case, because that depends on the actual atoms which are under forming the bond, and if the polarity is less in that, if the electronegativity difference is less, then dipole moment will be very small or negligible, and in that case you won't see any dipole moment. So that is the nature of atoms also affects the dipole moment, and that also needs to be considered. And the classic example is this NF3 and NH3. So example, NH3 NF3 both are C3V, but only NH3 has a significant dipole moment. So why? You know, because in case of NH3, this H and N, positive negative, this is dipole direction. See this dipole, so this is pointing, so this summation of these three dipole moments is pointing up, and this dipole moment due to the lone pair dipole, and the sum of NH dipole, both added up, so add up, and you have a significant dipole. So high value of dipole moment, whereas this is the dipole moment due to lone pair dipole. So this is, whereas if you are looking at NF3, you see that direction, this is now having a partial positive charge, this is negative, so direction of dipole is reversed. So some of these NF dipoles is pointing downwards. So NF dipoles नीचे की तरफ पॉइंट कर रहा है, और ये लोन पेयर डाइपोल ऊपर की ओर पॉइंट कर रहा है. So almost there is a very small amount of dipole is left. So because they are pointing in opposite directions, overall result is that you have a very small dipole moment in NF3 and a very significant dipole in case of NH3 because of the nature of the atoms that is bound to central atom. So hydrogen being more electropositive than nitrogen, and fluorine is more electronegative as compared to nitrogen. So this point is important. So NF, so it is such that NF3 wala jo hai na, so actual value, it turns out that it is, the values are almost very less. So because of this, you have the value is 0.024, whereas in this case it is 1.46 d by the magnitude of this thing. So this is also something to be considered. Similarly, if you go for by phosphorus pH bonds, phosphorus hydrogen has negligible, uh, there is no electronegative difference between phosphorus and hydrogen. So again, the dipole moment may not arise because of inner symmetry. So now we can also discuss about the chirality, the optical activity, how we can predict whether a molecule is likely to be uh, chiral or not. So chirality, you know what is, it is a Greek word which derived from chair, means handedness. So left, and so looking, when you look at the mirror images, so chiral molecules are distinguishable from their mirror images, just as our left and right hands. So chiral molecules and mirror images, we call them a pair of enantiomers of one another, and enantiomers are non-superimposable mirror images of each other. So this is the symmetrical relationship that that uh, they polarize, they rotate the plane of the polarized light which passes through them. So such molecules are said to be chiral. Whenever you have this situation that the mirror image is not superimposable on the original original molecule, then we say that the molecule is chiral, meaning this, we cannot superimpose this. So the symmetry element that prevents a molecule from being chiral is the SN axis. So when we are looking for chirality, we are trying to find whether is there any SN axis present. SN axis is improper axis of rotation. So symmetry elements present, for example, a point group which is having Cn and sigma h. If you have Cn and sigma h, then there is always an SN will be present, because rotation followed by reflection, this is what we do. And so in a perpendicular plane, reflection in a perpendicular plane, so Cn axis and a sigma h plane is the same thing, a rotational axis and a perpendicular plane, mirror plane. So if these two symmetry elements exist individually in a molecule, then Sn axis is definitely present, and that molecule is not chiral. Similarly, a center of inversion means an S2 axis. So we have also seen this S2, S1 means S2 is equal to I. We have already shown it earlier. S1 is equal to sigma. So we have already discussed these 2 points. So in a similarly, what we say that a molecule is definitely not chiral if it has a center of inversion or mirror plane. Or in simple words, you cannot have S1, S2, Sn, any Sn axis. So a molecule is chiral if it doesn't have any axis of improper rotation. No Sn axis present, then the molecule is chiral. So this is a simple rule that we get from this. It's a simplified thing which we can obtain. So if a molecule if you find that if you no SN axis is present, then the molecule is identified as uh, yeah. So this point is important. We have to look for SN axis, and if no SN axis is present, then so symmetry elements are absent if there is you have to be uh, if so you have to check for any SN axis that is present. If your analysis tells you that there is no SN axis, then you are sure that it is chiral. So in that search for this thing Cn and sigma h, okay, so presence of a mirror plane means you are having an S2 axis like that. So a simple rule of thumb is that, yeah, you should not have. So if a molecule has SN axis, it is not chiral. Simple. Very simply, if we place that conclusion, it is like this. So no SN axis, you are there. It is chiral. Other way around. So this is a simplest amino acid, one of the simplest amino acid, alanine, which is you can find. So this is also carboxylaldehyde. These are biological. So you can see, you can find any mirror axis. You can SN axis. No, then they are chiral. S1 is a mirror plane, sigma. S2 is the center of inversion. Hence, molecules either mirror plane or center of inversion have improper axis and cannot be chiral. So molecules with I and sigma are usually chiral, and they belong to S2N point group. So there is one more point that you will find in when you're reading F.A. Cotton's book. There's also a term called dissymmetric. So when the molecules are not superimposable, we call them, they are not superimposed on their mirror images, they are termed dissymmetric. There's also a word called asymmetric. So asymmetric is a little bit avoided because literal meaning of asymmetric is having no symmetry elements at all. Okay, and by that meaning no symmetry, when we say asymmetric, that means no symmetry elements, which means that it is a point group belonging to C1, which has only E, no symmetry element is present in C1. So it is important to see here that so all asymmetric, so a molecule belonging to C1 will also be dissymmetric. अगर एक C1 है point group को belong करता है, just like carbon attached to having different H, Br, Cl, F. अगर ऐसा है carbon molecule, so this is a C1 point group. So this is definitely its mirror image is not superimposable over this. This also doesn't have any symmetry element, so this is asymmetric, and it's because it is its mirror image is not superimposable, it is also dissymmetric. Okay, so asymmetric means you do not have any symmetry elements. So all asymmetric molecules are dissymmetric, that is you cannot they are non-superimposable mirror images. But the converse is not true. That means because in a dissymmetric elements, just as other cases that we have pointed out, molecules, you do have some symmetry elements present, only that improper axis is not present, but there are other symmetry elements, they are present. So you only, the requirement is that you need to be dissymmetric, non superimposability over the mirror images, and any such thing. So asymmetric and dissymmetric, these are the terms that you need to be learning. So the thing is that all symmetric molecules are dissymmetric, but all dissymmetric molecules are not asymmetric. Okay, so that is the way of expression. So a molecule that has no improper rotation axis is dissymmetric, and this is chiral. So this is the criteria for chirality, or we simply say SN axis, absence of any SN axis is the the molecule is likely to be chiral. If there is no SN axis present, it is chiral. So now you can work out some of the assignments. So what are the which one is, so draw boric acid in 3 different conformation. ये आपको draw करना है boric acid का. Which one is chiral, and then tell us which one will be chiral, which will not be chiral, how and why. O2F2. So we'll start with group theory, the mathematical part, in the next class. ठीक है, we will once you are so you now understand how it is helping you in finding which molecule can be polar, which molecule can be optically active. So group theory, this idea of point groups is and symmetry elements is helping you in a big way. Okay, so only those elements, so as I told you, कहाँ गया? So S2 and point group molecules without ion unless they belong to an ion sigma are chiral. So okay, so that's all for today. फिर हम लोग मैथमेटिकल पार्ट पे जाएंगे अबाउट दिस. हाँ जी, ग्रुप्स. कल का ग्रुप थ्योरी का शायद रह गया था, वो हुआ नहीं था रेफर. अभी एक दो बार दिक्कत हुई है ऐसा.